We have Professor Weissman here to teach you all about that. So give Professor Weissman a round of applause.
So now, if I wear that, I can move around those.
Yeah.
Okay. I want to make sure this wasn't constrained anywhere.
Now we've got the camera to follow you too.
Oh, that's pretty cool. Hey, look at that guy.
Where's the slides at, Russ? Or are they in your laptop? Or?
Oh, I don't do slides.
Oh, you don't do slides?
Clear the board.
Oh.
Oh. You want a sound check? Testing 1, 2, 1, 2. Testing 1, 2. Can I erase that? That's not. I need your help. You're taller than that. Go get. It's very tall. Oh, yes. We need those. Thank you, thank you. Are we live on the stream right now? Do we know how many people are watching live on the stream? One person? Why can't they just come in today? All right, ladies and gentlemen, some of you I know from passing the hallway, some of you I know from multiple classes. It's a pleasure to meet everybody. I always love to come and talk at these club meetings, formerly under a different name. This is my debut at, is it RITSEC or RITSEC? RITSEC? So before I begin, I want to tell you a couple of quick stories that happened to me over the summer. Summer's technically still going on until 21st or the 22nd. But early on in the summer, my family and I, my wife and our 2 kids, we live in Brighton. And there happens to be a nice influx of new people moving in the neighborhood every now and then. And we like some of those families that moved in over the summer, and we didn't like some of the other families that moved in over the summer. So my wife made a couple of welcome packages with candy and fruits for one of the families that we especially liked. We met them at Weissman's. We hit it off. They have kids our kids' age, and we wanted to become friends with them. So my wife made this care package, and she said, "Jonathan, go give this care package to the Smiths." So on our street in Brighton, a few houses recently went up for sale, and I wasn't sure exactly which house the Smiths lived in. So I needed to get the care package. I couldn't just look at the signs and say, oh, there's a house that just sold, because we didn't like some of those other families. They were shady looking, and they were quite frankly, nasty people, so we didn't want to associate with them. So what I did was, this was at 11:30 p.m. on a Sunday night. I'm also a musician. I got out my 500-watt amplifier and a microphone, and I blasted it, and I said, "Bob Smith, which house are you here on our block?" And everybody in the neighborhood, everybody in the state of New York probably heard that, and pissed off a lot of people. I woke up my kids. My wife was like, "Shut the hell up. Kids are sleeping." I'm like, "Nah, you told me to get this package to the Smiths. I know his name. I know his name is Bob Smith, but I don't remember exactly which house he lives in. I know that a few houses went for sale. I want to get it right to the Bob Smith house." So what happened was, like I said, I woke up my kids, woke up everybody in the neighborhood, but you know whose attention I did get? I got Bob Smith's attention, and he very discreetly walked over to me and said, "Idiot, it's 123 Main Street," and then walked back to his house really quickly, not wanting to associate with me because I was not in good favor with everybody else in the neighborhood at the time. So later that night, after I got his street address, I walked that package over to his house, and everything was fine. That's story number 1. That's a cool story that happened over the summer. Russell, what do you think about that story? True story. Story number 2, before I get into networking. And by the way, this is not really just networking 101. It's like networking 101 all the way up to graduate level in a very condensed format. Just know that this is a highly compressed lesson coming your way with a little bit of everything. But story number 2, we did a lot of traveling over the summer, And I'm originally from Staten Island, New York. My wife comes from Philadelphia, Pennsylvania. So I logged a lot of miles on the car. And then we got back to Rochester out of one of our many car trips. And we emptied out the bags. And I see something shiny in one of the bags. And it's my mom's candlesticks. And I said to my wife, how did these get in the bag? She's like, I don't know. Then I said, no, Jacob, come here. Kids came over. And I said, do you know about this? One's 4, one's 6. And Jacob actually said, yeah, they're really cool. They're really shiny. I took them. And I said, you klepto. And then I checked my email later that night. I had a nasty email from my mom that said, did your kids take my candlesticks? And I said, in reply, yeah, I'll get that back to you. But I was not about to drive 6 hours, 350 miles down to Staten Island, New York again. Get this. What I did was I Googled for the nearest UPS store. It came out to be the UPS store on Elmwood Avenue, 12 Corners in Brighton. And I brought the candlesticks in a brown box to the store and signed the paperwork, gave them some money, and then I left the package there. And it was up to them to get the actual package back to my parents in Staten Island, New York. That's story number 2. Scott, what do you think about story number 2? Great story. What I just told you is how every form of networking communication works. The very first thing a node, and node is just a fancy word of any device on a network with a logical IP address. Any node that sends traffic needs to determine one thing right from the start, and that's if the communication is local communication, which means meant for another device on the same network, or remote, which means meant for a device not on the same network. It could be 2 routers away. It could be 20 routers away. You have to determine if you're sending traffic, number 1, if it's local or remote. So in story number 1, I determined that Bob Smith was local to where our house is. So I decided that it's up to me. I'm going to take the package to his house. It didn't make too much sense for me to take that package to the UPS store. Story number 2, I realized that my parents in Staten Island, New York, are a little bit far from here in Rochester, New York. So I wasn't about to directly deliver the traffic myself. I needed to send it to my default gateway. I needed to have a router send it to another router, to send it to another router as the UPS routing goes, eventually till it got back to my parents' home in Staten Island, New York. So as far as the networking goes, and taking the fun stories out of the mix, and sorry to ruin any surprise, but those actually did not happen. So when dealing with networking, how does a device that needs to send traffic determine whether the traffic is local or remote? Well, let's start off talking about a logical IP address. They are 32 bits long, and if you ever have a problem with binary, you got to get yourselves one of these nice binary watches. I got a binary clock in my office as well. But everything networking and a lot of things cybersecurity deal 100% with base 2 binary. There's a lot of hex, base 16 as well. So I'm going to start off by throwing some bits on the board that look like this. I think there are 32 there. Can somebody tell me what the IP address in base 10 is represented by all these 1s and 0s here? Yes? 10.0.0.1. Ooh, invisible ink. That one doesn't work. Oh, I'm going to need that later. 10.0.0.1. Absolutely. One of my favorite binary numbers is 10.10. The 8's column is on and the 2's column is on. That translates to base 10.10. So let's say I'm sending traffic in story number 1. Me with that actual brown box. Maybe my wife didn't make the care package in a brown box. Maybe it was some form of clear plastic. I had to give to the Smiths to welcome them into the neighborhood. So what I did was I had to first, in order to determine whether the destination was local or remote, I had to figure out where the hell I was. I had to figure out my local network. So here's how the sender of all traffic determines where exactly he is, what device on what network is represented. So the host with this following IP address of 10.0.0.1 takes his IP address, and you should also know that IP addresses come in 2 parts. The very first part of the IP address is known as the network ID, which identifies the network you're on, And all devices on the same network share that initial number of bits to be determined. It's not black and white. It's not like we had in the days of class full addressing back in the early 90s. Nowadays, since the 90s at least, everything networking has been very classless. If somebody stops you on the street, says, are you a classy person? If you're into networking, you say, no, I'm very classless. So we don't know where that breakup is of the network ID and the other part of the IP address known as the host ID, which is a specific string of ones and zeros that every device on the network has in a unique format. You need to uniquely identify yourself, but you also have to identify yourself as part of a larger overall network. The other entity that will allow a host and a router and any other device to determine what network this host is on, something called a subnet mask. A subnet mask is also a 32-bit looking address, but the difference is subnet masks always follow this pattern. A string of ones followed by a string of zeros. Anytime you've got a 1 in the subnet mask column corresponding to a bit in the IP address column, that means it's a network bit which is shared by every device on the same network. Every time you've got a 0 in the subnet mask column corresponding to a bit in the IP address, that means it's a host bit, which means it's unique. That whole string of host bits are unique in entirety to every device on the network. Can you do me a favor? If you're a male wearing a hat, stand up. 1, 2, 3. Oh, all my old friends there. Hey, I haven't seen you in a while, John. Why don't you stand up? Doesn't have a hat. Any females with hats? Why don't you stand up? Not male, not wearing a hat. So these guys right over here, oh, there's a, no, that's a hood, and then it's a male. So 0 for 2. So these are the only, okay, have a seat. Round of applause for our participants. What logical Boolean operation did I just demonstrate? AND, which means the host, to determine what network he's on, takes his 32 bits of IP address and his 32 bits worth of subnet mask, performs the Boolean AND logical function, and what comes through, if you logically AND all those ones with these bits and all these zeros with those bits, is something that looks like this, 10, 0, 0, 0. Definitely, if we got a bunch of zeros over here, it doesn't matter what the IP address bit is going to be, because the only way to produce a 1 in a logical AND process is to have 2 ones. Every other pattern produces a 0. So this thing right over here that I circled, 10, 0, 0, 0, represents what? What does that represent? Jonathan, cool name, former student of mine. What does that represent? See? Picked them off first base there. It represents the network ID, the identifier for the network. It's not an assignable address to any host. You can't say, my name is Rochester Institute of Technology. You could say, my name is Bob, and I go to Rochester Institute of Technology. This is a non-assignable address that represents the network that the host is on, because if the host is to determine whether communication is local or remote, it's got to determine what network he's on. So that's step number 1. So far, so good? So let's say the host has traffic for this guy right over here, Mr. 10002. The host, once again, the source of traffic, is going to perform that Boolean AND function. Stand up if you're a male wearing a hat. You don't have to do that again. Or AND wearing a hat. And the logical AND process for the subnet mask, which, by the way, I've got in binary over there. Turn that into base 10. It's going to look something like this. 255.0.0.0, or for those of you that speak Apple cider notation, /8, which means the first 8 bits are network bits and the last 24 bits are host bits. So these are the same. What does that tell the sender of traffic? Same network, which means they're on the same network. He could deliver the traffic himself. That's how, in story number 1, when I saw that Bob Smith needed to get that package, I was able to deliver to him directly myself without requiring the help of UPS. That's story number 1. But in story number 2, let's say the destination IP address is 11.0.0.1. When the source of traffic applies the same subnet mask that he has. By the way, he doesn't know what the destination mask is, nor does he care, because if they're on the same network, also known as LAN, also known as subnet, the masks are going to be the same anyway, so it doesn't make a difference. So logically ANDing these two together, you get 11.0.0.0. What does that tell the source of traffic? Remote, not on the same network. He needs to take the box to UPS, or more technically, he needs to send his traffic to his default gateway, the router interface on his network responsible for taking all remote traffic off of the network and bringing all remote traffic back onto the network. We'll talk more about that in a couple of seconds. Any questions so far? So now I've established the technical nuances of story number 1 and story number 2. Let me also tell you right now that container, the chunk of data being sent that includes these IP addresses from a networking perspective is something called a packet, which people just almost call every form of network traffic, which is incorrect. This is an IP, an Internet Protocol packet, and it looks like an envelope, something like that, not really. On the front of this envelope, the source is going to put his IP address, which is 10.0.0.1. We'll do local communication first. Source takes his IP address, puts it on the envelope, and that's the source IP address. Then the source takes the destination IP address and puts that on the envelope as well. Inside the envelope known as the packet, we'll see some other stuff will be placed inside the envelope very shortly. But we're just dealing with the addressing right now. Something very important to understand about networking communication, packets never move by themselves. You'll never see a packet moving by itself. The packet always has got to be encapsulated inside of another container. Something that looks like this. Or this. By the way, am I moving too fast, Mr. Cameraman? Don't want to be a blur. So here is the packet containing what we call the logical IP addresses. Packets never move by themselves. Packets move in other containers known as frames. So you put the packet in the frame, and then you send the frame. Packets never move by themselves. The frames differ by the infrastructure that you're on. In other words, let's say I had an envelope, a regular envelope, and there was a check in there for Russell, and I want to give Russell $500. I put the check in this envelope, and then I wouldn't send this envelope by itself. That wouldn't be too secure. People could look through. People could open it up. I'd go get one of those cardboard boxes, whether it's at the USPS or DHL or FedEx, and I'd put this envelope in that outer encapsulating envelope, although I'm using a canister for my little example right over here. And this envelope would say, from Jonathan to Russell, but the outer encapsulating container will actually have my address and his address specific to where we live. Yes?
Can you hide the source IP, or is it always going to be on?
You could spoof your IP address, but then you're not going to get any return traffic. Spoofing back in the day was easier with an extension to the IP header that I'll tell you about in another class that you take with me. But in other words, if I write a letter to you and I don't include my correct address in the upper left-hand corner, I'm not getting a reply. Simple as that. So here is the packet. Here, the packet is encapsulated in the frame. If we're using USPS, we use the USPS cardboard. If we're using DHL, we use the DHL cardboard. The two most common types of frames found today are frames for wired networks, known as Ethernet. So let's say this is an Ethernet frame right over here. But if I'm on a wireless connection, you're not going to be using Ethernet on a wired connection, neither will I. You get a different frame, and this other frame in the world of wireless communication is an 802.11 frame. But notice that the packet inside either one of these two frames is the same packet. It hasn't changed. It's the same IP packet encapsulated in either an Ethernet frame or an 802.11 wireless frame. But the problem now is as follows. There are logical addresses that tie these devices to networks inside this frame, the frame itself needs some addressing as well. And there are 2 more addresses found on the frame. So if we're making a scoreboard right over here, source IP is going to be 10.0.0.1. The destination IP is going to be 10.0.0.2. We need 2 other addresses known as MAC addresses. Stands for Media Access Control, and these addresses are very different than IP addresses. Number 1, instead of 32 bits long, they're 48 bits long. Number 2, instead of being written in base 10 notation, we write MAC addresses in base 16 hexadecimal notation. So since 4 bits make up 1 hex character, there are 12 hex characters, because I told you that there are 48 bits. 48 divided by 48 divided by 8 is 6. And now when you have a MAC address consisting of 12 hex characters, the first 6 are known as the OUI. Stands for the Organizational Unique Identifier, which means if you're a NIC, a Network Interface Card manufacturer, NIC is the chip, although people still say Network Interface Card, and hasn't been an expansion card for like 8 decades already. I've tried to start a revolution by calling it Network Interface Chip. Nobody really caught on. Everybody still says Network Interface Card. But you could actually say something worse than that. You could say NIC card. That's like saying ATM machine. That's even worse. So the MAC address consists of 12 hexadecimal characters. 12 times 4 is 48. Those are your 48 bits. And like an IP address, a MAC address is divided up into 2 parts. Part number 1, the OUI, the Organizational Unique Identifier, which means the company that manufactured the NIC has their own unique 6 hex character pattern. And then after the OUI comes something called a device ID, which is like a serial number assigned to each NIC that they make, so that no 2 MAC addresses will ever be the same. So if you look at the comparison over here, it looks very similar. The 2 parts to MAC address, there are 2 parts to an IP address. But here it's always line in the sand, half and half, 50-50, 6 and 6. Here it varies based on the subnet mask until you get to IPv6, where you deal with 128-bit addresses, and that is split in the middle like MAC addresses. You'll only see 64 bits representing the network and 64 bits representing the interface, but that also is a story for another day. So right now, this device, Mr. 10.0.0.1, knows what his IP address is. He also knows what his MAC address is, because it's burned into the NIC that he's using. So let's just keep it simple, stupid. Instead of having 12 hex characters, I'll use 3. Let's say the source MAC address is AAA. But the problem now is the source needs to get that last piece of information, the destination MAC address. The first 3 are always going to be known. If you don't know what the destination IP address is, a cool little protocol called DNS will help you out. We talk about that in Net Services for about 8 weeks. So the destination MAC address, that's the only unknown variable right over here. And the host, the source of traffic, needs to figure out what it is. So in the mail the other day, I got one of these cards. Read this to everybody.
AARP.
Just pronounce it. Don't ARP, right. So I'm not that old. It doesn't have my name on it. It says valued member. It doesn't say Jonathan Weissman. But you can't do IPv4 without this card. There's no such thing like this in IPv6. But this card is absolutely necessary for networking in the world of IPv4, because ARP, Address Resolution Protocol, is used by devices to take a known IP address and associate it with an unknown MAC address of that same device. For network traffic, you need 4 out of 4 addresses to send traffic from a source to a destination. The absence of one will necessitate this protocol to spring up in action. And what the networking device does at this point is he sends a network broadcast that says, hey, everybody in the network, stop what you're doing. I don't care what you're doing. If your IP address is 10.0.0.2, I need your MAC address. Who hears that? Everybody in the network. Who cares about that message? Only Mr. 10.0.0.2. It's like me giving a class a 500-page PDF, and I say, class, read this for homework, and then on the very last page it says, Jack McKenna is only for you. And then everybody else would be pissed. Like, this guy gave me all that stuff to read, and it wasn't even for me in the first place. That's the only way to do it in IPv4. Again, IPv6 revolutionizes this in a far more efficient way, but devices are constantly interrupted with what they're doing with ARP requests, which are broadcasts. How does that relate to my first story?
You're broadcasting it out to the entire neighborhood when instead you got a multicaster to find the people that matter.
Right, but this is an IPv4 story. Hey, everybody! If your name is Bob Smith, I need to know what house you moved into. I disturbed everybody in the network. But you know what? As disturbing as I was for everybody else, I still got the attention of Mr. Bob Smith. So when the ARP request is sent, it's broadcasted. When the ARP reply comes back, remember what I said? Bob very discreetly walked over to my house and said, hey, idiot Weissman, it's 123 Main Street, and then walked back away again. He has my MAC address at that point because of this ARP request. He doesn't need to ask me what my MAC address is. That's why ARP replies are always unicast. Unicast means one source, one destination. Broadcast means one source, and everybody on the network has a destination. And of course, in the middle, you've got multicast, which means one source and multiple destinations, but not everybody. So now that the ARP reply comes back with the MAC address, in this case, the shortened MAC address of BBB, source is able to put the destination MAC address on the frame and send it on to the actual destination. In the remote communication example, the source will see that the destination is on a different network, and he'll still send an ARP request, and it's still a broadcast. But the ARP request doesn't say if your IP address is 11.0.0.1, I need your MAC address. The ARP request doesn't take the actual destination into account because you only talk directly to devices on your same network. Just like I wasn't going to drive 6 hours back to my parents' house in Staten Island, New York to deliver those candlesticks. I needed something closer for me, and I needed to rely on somebody else. So looking at his IP configuration, the source sees the IP address of his default gateway, and he actually sends an ARP request that's broadcast looking for the MAC address of the router's interface on his network. Let's say that's RRR. Of course, R is not a hex character. And what's going to happen is the ARP request will go directly to now all devices on the network, but the router is the one that's of interest. The router will send an ARP reply back, and the router will take care of the actual transmission of the network traffic. Devices that connect nodes of the same network together, depicted by a rectangle in most networking diagrams, is a switch. A switch connects devices of the same network together. If you're thinking of the H word, don't say it in my presence. Routers don't connect devices. Switches connect devices. Switches connect different components of the same network together. Routers don't connect devices. Routers don't connect end stations or nodes. Routers connect networks together. So in the little story example, the router would be the UPS store. And what routers do is they use protocols like OSPF locally or BGP more remotely to send traffic to the final destination. It's a good movie. You ever see those? Final destination. And that's how routers get your traffic off of your network to another network, to another network. That UPS store on Elmwood Avenue in Brighton, it didn't care about my parents' home address. It didn't know my parents' home address. Who did that UPS store need to get that brown box to? It wasn't my parents. Next UPS store, Syracuse. We're skipping places now. Manhattan, and then Staten Island. So each router is only concerned with getting it to the next router on its list, going down eventually to the actual final destination. So IP addresses and MAC addresses, very, very important entities of all networking communication. But there exists another form of address that we still need to talk about. Question?
How does the router have to perform a search through all the available routers every time in order to get through the end?
Guys, I can't concentrate. So if you want to talk, please step outside. Routers contain entities known as routing tables, which are lists of destination networks that they can send the traffic to. Of course, it's impossible to list every network in the world in your local routing tables, which is why locally routers that are running OSPF have a default route in most cases to an ISP to get the traffic there. Now, internet backbone routers running BGP have upwards of 750,000 routes and destinations in memory that they use to reference, which is why IPv4 is not as efficient as IPv6 is already going to be. That's also a story for another day. But the point is, when a router sees a destination network associated with that routing table entry is the next hop, the next router to send the actual packet to. So the UPS store on Elmwood Avenue will have a next hop UPS store for traffic destined for New York City. But that's not the end of the story, because in the event that the destination network is not known by the router, there's a default route, which means send it to this router, sort of like a, I don't want to use the H word in that networking sense, but like a hub distribution, hub spoke facility where you send all the mail to Buffalo, and Buffalo will figure out where it goes after that. Okay.
I've heard the term collision domain and broadcast domain get thrown around. What are they exactly?
Collision domain doesn't exist anymore today because of that S word, the switch. Back in the day, now you're forcing me to use the word hub again. Back in the days of hubs, when a device sent traffic into that device that connected everybody in the same network together, there existed the possibility that other traffic would be going in and out of the device at the same time. When two messages went in the hub at the same time, they blew up. That was called a collision. We don't have that with switches because switches use a technology known as full duplex, which means you can send and receive at the same time, and each switch port connected to each NIC is its own collision domain. Back in the days of hubs, everybody was on the same big fat collision domain. It's like I was trying to talk and other people in this room are talking. I can't hear myself talk. Our messages collided. We don't have that problem with switches. So far, so good?
Sure.
Broadcast domain still exists today. Doesn't in IPv6. In IPv4, it still exists. Broadcast domain means when you send a network broadcast, who hears it? And a broadcast domain is quite simply your LAN or your network or your subnet that you're limited to, for the simple reason that routers never forward broadcasts. Because if routers did forward broadcasts, a broadcast could go around the world and back and obviously saturate a lot of bandwidth and take up a lot of resources. Routers, when they see a destination broadcast address, they just drop the traffic, whether it's at layer 2 with MAC addresses or layer 3 with IP addresses. In IPv6, there's no such thing as broadcasting. It does not exist. Good? Okay. So back in our little story over here, if I was to tell you that there is a networking model that I am really quickly glossing over, it's the Open Systems Interconnect model put out by the ISO organization, which does not stand for the International Standards Organization. It stands for the International Organization for Standardization. I'm not dyslexic, but the ISO word is a Greek word that means equal, which is what all standards bodies look to promote. There's an RIT course on the catalog that actually expands that incorrectly, like nails on a chalkboard for me. It doesn't stand for anything. It just means the word equal. But of course, they came up with the Open Systems Interconnect model, not to be confused with the Cisco iOS. And Cisco, by the way, said it used to be Internetworking Operating System, and now it just stands for iOS, like when Prince went to Simple, don't expand it. Not to be confused with this iOS, where the I actually doesn't stand for anything. So it's a lot of fun with all those letters right over there. So at layer 2, we've got MAC addresses with the frames. At layer 3, we've got IP addresses with the packets. There's another form of an address found at layer 4. But before I tell you about that, let me tell you about major protocols that are found at layer 4 of this OSI model. There are 7 layers. I'm not going to take you well beyond layer 4. One protocol is known as Transmission Control Protocol, TCP. Another very well-used protocol at this layer 4 is UDP, User Datagram Protocol. Let me tell you the differences between it. You tell me which one is better. Anybody ever hear the expression, there are 2 things guaranteed in life, death and taxes? Well, no, that's not true. There are 3. It's death, taxes, and TCP. TCP is right up there with death and taxes as an absolute positive guarantee for error detection and error correction. Now, of course, if Russell takes a sledgehammer and knocks my laptop out, all bets are off. or if Scott takes a pair of scissors and cuts my Ethernet cable, it's not guaranteed. Assuming that there is a viable bandwidth connection between two devices, TCP guarantees that every bit sent by the source will be received and acknowledged by the destination. If it's not, it's sent again. It's connection-oriented. It's guaranteed delivery. That's TCP. UDP is unacknowledged, unguaranteed, and connectionless. It's like you put a stamp on an envelope, you put it in the mailbox. If it gets there, it gets there. If it doesn't, it doesn't. You don't know that it didn't get there, and the destination doesn't know that you sent it. That's UDP. TCP is you get one of those return receipts from the USPS, green and white sticker. You put it on, and they have to sign for it. And if you don't get that return receipt back, you know something went wrong, and you could send the message again. Any freshmen in the room right now? Freshmen? You're a freshman. I hate freshmen. No, I'm just joking. That's UDP. So if the messages don't reach the destination, I don't know they didn't get there. If he doesn't get it, he doesn't know that I sent it. That's exactly how UDP works, but it's more fun to throw markers and scare freshmen. Here's TCP. Am I out of markers? Here's TCP. Can I have a couple in the back, actually? That's not part of UDP. Thanks. Ooh, that was almost very fatal for my shirt. Another freshman. Don't worry, I won't hurt you. What's your name? Trey. Trey. Hi, I'm Jonathan. Can I send you some markers?
Sure.
Okay, that's a perfect response. Very good. Now say, can I send you some stuff as well?
Can I send you some stuff as well?
Sure. Say I got the green marker.
Got the green marker. Got the red marker.
Oh, that was a good shot there. Keeping Mike on the side. See, he doesn't say I didn't get the black marker because he doesn't know I sent the black marker. So I'm saying, using my binary calculations over here, he got the first two. I haven't heard back that he got the black. I got a copy of that in RAM.
Got the black marker.
So that's TCP, where it's guaranteed, acknowledged, connection-oriented data delivery. So let me ask you again, which one is better, TCP or UDP? Ali, let me ask you a question. You can say that. You don't have to come up. Everybody know Ali?
Yeah, it depends on the traffic. Which traffic are you?
That wasn't the question I was going to ask you.
Okay, no problem.
I was going to ask you, what are you going to wear when you're 95 years old? No, you actually answered the question already. Why? What are you going to wear when you're not 95 years old? Nobody wants to go there?
A diaper.
Okay, be more specific. Depends. Depends. Okay, so Ali again. Now for your original answer. Which is better, TCP or UDP? Playing it safe. The answer is it depends, of course, because FTP, email protocols like SMTP, SSH, HTTP, SSL, TLS, these are all protocols that exist at layer 7 that require integrity, where one bit that's off or lost could corrupt the entire message. So for protocols like those, it makes more sense to use TCP at layer 4. But when you're talking about VoIP or DNS, DHCP, some other major protocols, where if you miss a message, like with DNS or DHCP, you'll ask it again, or in a VoIP stream, if part of that stream, whether it's audio or video, or audio and video, whether it's a live video stream, whatever it is, if you lose part of that message, it's only a small moment in time. You might notice some small degradation in quality. You might notice some audio glitch. You might notice a video glitch. But you don't want to go through all the overhead that TCP requires, as we did over there, to send and receive phone calls over the internet or video streams, because that would make the communication undesirable. It's like somebody says hello, and somebody on the other side says, hi, how are you? but the hi, how are you part doesn't reach the source, or the I got your hi message doesn't reach the source, and the source will just send that same traffic again with some filter in place for the return traffic. You can't work like that. So UDP is used for real-time streaming and major protocols like DNS and DHCP. If you ever have a professor who doesn't answer your questions in class like I do, my best advice, if they ignore you, just raise your hand and ask again. If you ask your DNS server a question, if you ask your DHCP server a question, and something happens with the message, it gets lost, whether it's the question or the answer that gets lost, you ask again. That's why DNS and DHCP, two major protocols used on all networks today, use UDP as their layer 4 protocol. So far, so good? Now, as far as the marker thing goes, I do have a technical explanation for that as well. So these were actual blocks that our oldest son Noah was playing with, and we were, ooh, see, that's a collision or something like that. That's message corruption right over here. So what happens is, wow, this thing is going insane. Can you still hear me? See what happens when you bring props and you try to be funny? Can you hear me still? Something happened with the wire. Jack? Okay, okay, fine. Okay. So what am I looking at over here, if I can actually keep these together? Can anybody tell me what we're looking at over here? Besides my kids' blocks that I stole. I actually bought them another set to replenish the supply. What we're looking at here, see that blue stuff? That's the frame at layer 2 containing the source and destination MAC addresses. What's inside the frame? The IP packet right over here. What's inside the IP packet? Either the TCP segment, as we call it, or the UDP datagram, as we call it. So instead of bringing a bunch of Russian dolls to class today, I brought my blocks over here because it's the same concept of encapsulation from the OSI model. And see that yellow stuff? What would you describe that yellow stuff as?
The payload?
That's the payload. In fact, each of these is payload of the previous layer, but this is like the FTP stuff, the SSH stuff, the DNS stuff, stuff that exists at layer 7 of OSI. So with that said, as far as TCP goes, I want to focus on what TCP and UDP have in common and where they differ. The only thing they really have in common are 3 fields. I want to focus on 2 that are actually in common for our little lesson today, called ports, another form of addressing at layer 4 that's found. You ever see one of those mailbox grids in an apartment building? Where are my markers? There. And there's a guy who lives in apartment number 21, and there's a lady who lives in apartment 80. And if you wanted to send the guy in apartment 21 a letter, you'd have the same street address as the lady in apartment 80, but for the guy, you'd write apt.21, and for the lady, you'd say apartment number 80. Let's say you've got 2 server services that are running on the same machine. They have the same IP address, have the same MAC address. How does the traffic for the FTP server get to the FTP server? And how does the traffic for the web server, the Apache web server, get to the actual web server? And that's the answer here, the only important common feature between TCP and UDP. They contain another form of addressing known as ports, which are numbers that represent a logical connection from the operating system to a service that's running on that actual operating system. So in our little example over here, let's say the guy in apartment 21, his name is Frank, and the lady in apartment 80, her name is Helen. Can anybody tell me what Frank's full name is? Or potential full names for Frank? No. Frank Thomas Peterson. You want to fill in the blanks for Helen? She's got a couple of middle names. Let's say Helen Teresa Thomasina Parker. Which means on one machine you got an FTP server and you got an Apache web server. If the destination port is 21, the OS hands off the traffic to the FTP server, to the FileZilla FTP server. If the destination port is 80, the web server gets the traffic from the operating system. because how else will you be able to distinguish them? You can't. Same IP address, same MAC address. That's how TCP and UDP are similar. Here's where they differ. TCP has these things called flags, like this one. Flag is on or the flag is off. These are individual bits. There are 9 TCP flags, but 6 of them are major. So in the TCP header with these flags, in order to establish a connection from source to destination, the source, when he sends traffic to the destination, raises the SYN, which is short for synchronized flag. The destination says, I acknowledge your request for synchronization. That's like when he said, yeah, you can send me traffic. And then he needed to send traffic to me. So he raises the SYN flag himself. And then in step 3 of what we call the TCP three-way handshake, source says, let's rock. This is the taxiing of the plane before takeoff so that the two sides have an established connection for a guaranteed, acknowledged, connection-oriented communications pathway. UDP doesn't do any of this. There are numbers that are involved. Initially, the source comes up with some pseudo-random 4-byte number. Let's just call it 8 right over here. The other side, in order to prove that he really got that request for synchronization, increments that value by 1 and comes up with his own pseudo-random value, let's say 77, which is now incremented by 1 on the other side. And after this point, after those numbers have been initially set, every damn bit that's sent, technically it's a byte, will increment those numbers so the source knows how much data was sent, the destination knows how much data it got, and the destination also could do error detection and error correction by looking for gaps in the numbers. UDP doesn't do any of that synchronization stuff that you're taking a look at.
How much faster is UDP? It doesn't have to go through all this back.
Significantly faster, number one, because it doesn't have this overhead, but it's also significantly faster because the UDP header only has 4 simple fields. The TCP header can range from 20 to 60 bytes. That's a lot more than the 8-byte UDP header. So it's the way it works and the size that matters as well. So it's quality and quantity that make UDP a lot more efficient. But again, applications choose it, not humans. No FTP server would ever use UDP because their integrity is more important. You'd rather slow down the communication to get it right than rush it. Whereas with VoIP and any stream, you want to rush it, and if you miss something, that's fine. Just keep going. So those are the layer 4 protocols, TCP and UDP, that are used, that are encapsulated inside of the IP packet. And again, the IP packet is encapsulated inside of the Ethernet frame. It's all encapsulation right over here. Now, something like this, of course, can be abused from a cybersecurity standpoint because the way into a machine and the way out of a machine physically, those ones and zeros, those pulses of light or electricity coming into a machine, how do they get in and out of the machine physically? The NIC, the network interface card. Logically, the way into and out of a machine is through a program. Program, let's define as a bunch of code that follows algorithms to solve problems or accomplish tasks. That's a program. A service is a program that runs independently of a logon in the background, like a workstation service or like a DHCP service that doesn't require a reboot. In the world of Linux, we don't use the term service. Linux has its own unique term for a service, which is a program that runs independent of a logon. Starts with a D, daemon. In Linux, we say daemon. In Windows, we say service. Both daemons and services are programs that run independent of a logon. Why am I telling you that? Because the way in and out of the machine physically is through the NIC. But logically, the traffic goes into and out of the machine, like we illustrated with the ports, through a program or service or daemon. How does the ones and zeros, how do the ones and the zeros get into the machine logically? Through these services or programs or daemons, through the actual ports. So if you've got a server running, we say that port is open. In other words, start your FileZilla server, port 21 is open. Start your Apache web server, 80 for unencrypted traffic, 443 for SSL, TLS encrypted traffic, they're open. The thing that really makes me really angry is when people say, and I do a lot of industry consulting, and I hear people in industry say, yeah, Jonathan, can you close that port with the firewall? I'm like, no, I can't. They're like, I thought you knew what you're doing. I'm like, I do, but firewalls don't close ports. Firewalls don't close ports. Firewalls don't open ports. Firewalls filter ports, which means if we're having an RITSEC meeting right here, and I'm teaching, and the room is on, the lights are on, room is very vibrant. Let's say this is a program. Let's say that the program is running. Let's say the port, you see that door over there? That's the port with a number on the front. We say this port is open. But let's say there's some big beefy guy downstairs at the Golisano entrance who only lets you into the building if you're wearing an orange shirt. That's the firewall. That's the firewall checking that you meet a certain condition to let you in or to not let you in. Or in a hostage situation where certain people are allowed to leave but other people are not allowed to leave. Firewalls don't open ports. Firewalls don't close ports. Firewalls filter ports, which means they say to some traffic, yes, you can come in, or no, you can't come in, or yes, you can leave, or no, you can't leave. Firewalls don't open ports or close ports. How do you open a port? You start a service. How do you close a port? You stop the service.
But then where does port forwarding come in? Because if you try connecting to an external IP by a port and
Port forwarding is just a mapping from a port that is globally known to your router who's doing the port forwarding to some other private inside IP address and the actual port on the system. If you set up a port forwarding rule and you don't have that service listening on the port, it does nothing. In other words, let's say I say, hey, what's your name? Evan, go to SecLab for me for a second. And let's say SecLab is locked. That's a port forwarding rule, but if the service is not started, you're just going into a locked door. Now, with that said, this original TCP construction of SYNs and ACKs and a bunch of other flags that I teach about in net services, it obviously can be used for bad today as well. Anybody ever hear the name Vint Cerf? Who's Vint Cerf? We call him the father of networking. He's one of the co-founders of the TCP/IP suite along with his buddy Bob Kahn from the Department of Defense. He came here a few years ago, and I asked him a very interesting question that I'm going to get to in a second. But before I tell you that interesting question, I got to tell you that if, again, you want to see what service is running on a system, you can use something called a port scan. A port scan is a probe that manipulates the good of TCP for diagnostics, for knowledge, information gathering, enumeration. Any word you want to throw works over there. Why is it important to know what services are running on a destination machine? Because the way into and out of machine logically is through a program or service. So you find out what's running on the machine. You find vulnerabilities that are associated with that service running on the machine. You find exploits that get you through those vulnerabilities, and then you exploit the machine itself. So there are many different types of port scans. The most common one, the default one used by a cool little program called Nmap, is called the SYN scan, which means a white hat ethical hacker, penetration tester, or a black hat hacker will send a probe to all the ports or some of the ports on a destination machine. And let's say I want to see if port 8080 is running anything. And then from that other machine, I get a SYN-ACK back. What does that mean about port 8080? It's running something. It's running something. And then I look further into the mix. If an open port gets a SYN, based on how Vint Cerf came up with the scheme, the open port will send a SYN-ACK back. But if an open port receives a SYN and sends a SYN-ACK back, normally the sender of the SYN will send an ACK back, as we saw over here. But if you're doing probing, if you're doing scanning, remember, the quieter you are, the more you hear. You want to be as stealthy as possible. So if you're probing and you're not sending normal TCP traffic, the source of the traffic won't send that ACK back. The source will send an RST, another flag in TCP, short for reset back, which means, no, never mind. I just was checking. And there's no application log of that probe. Now, of course, a firewall and IDS and IPS might have some form of a log, but this remains stealthy from the application's perspective. If you scan a port with the SYN scan and that port is closed, it sends an RST back. RST from a SYN means ain't nothing to see over here. Lights are closed, the door's locked. So I asked Vint Cerf when he came here a few years ago, I said, Vint, why did you make it? I mean, he's the father of TCP and the father of networking. I said, Vint, why did you make it that when a closed port gets a SYN, it sends an RST back? And he said, that's a good question. You asked that during your class often? I said, yeah. And you know, when a student asks me, I say, because that's how Vint Cerf wanted it. I was joking, of course. But the actual explanation that he came up with is very sound. Instead of not sending anything back, which increases latency and uncertainty and ambiguousness, the destination says, for a closed port, RST, which means ain't nothing to see over here, move on. And that's a quick way to minimize any latency that goes on between the source, the destination, and the network infrastructure between them. Using this method, it's very easy to see what's running on a machine, find vulnerabilities associated, find exploits, and then get into a box, of course, which is why patching and updating is also one of the most common themes you'll see in any cybersecurity class. Everything I talked about here today is 101 to 801 right over here. If you have any further questions, my office is just down the hall on the left. And I'd be more than happy to see some of my old friends, make some new friends. Come see me at any time. But we are limited in time today, so unfortunately I'm going to have to cut it short. Thank you for your attention.